let's see how we can situate programming languages, paradigms, and the concepts that they're made of. How these three things connect. So in fact, there are lots and lots of programming languages. Hundreds are used, as I said. And in fact, in your careers, if you're students, you will see very many. If you're already software developers, you have seen already a number of them. So there's a huge number of programming languages. But in fact, there are many fewer programming paradigms. The number of programming paradigms is much, much fewer because many languages implement or realize the same paradigm. So in fact, only around 30 different paradigms are used in practice. And in fact, each of these paradigms consists of a set of programming concepts. So the number of programming concepts is also a little bit less than the number of paradigms. But both the number of paradigms and the number of concepts is fairly small. So if you want to understand programming, instead of understanding hundreds of languages, it's much easier to understand 30 paradigms, and then you just see what the difference is in each language, how the different details of how they implement the different paradigms. So let's now take a quick look at all these paradigms. There's a lot of paradigms. There's 30, which is still quite a big number, and each one of them has its own way of thinking, its own set of techniques, books written about it, languages, and so on. So in a few minutes, I can't really say all of this, but we'll just give some hints at what's going on. So all of these paradigms, so all 30 of them, they have in fact much in common. Each one is based out of a set of concepts, and it has a kernel language. And in fact, often just one concept makes all the difference. Like what we saw in the course, starting with functional, adding either cells or threads gives you a whole different way of thinking about programs. Adding explicit state to the functional paradigm gives you object-oriented programming, lets you do all the different techniques of object-oriented programming. So this is actually a good way of looking at the paradigms, the concepts they're made of. And this will also let us see how they're related to each other. So with this, we can bring some order to the paradigm jungle. So here's some of the paradigms, not all 30, but a number of interesting ones that I've sort of randomly put on the page so you can see it's kind of a jungle. How do you bring order to all of these? There's very interesting ones. There's functional programming, there's the multi-agent data flow, there's concurrent object-oriented programming, there is lazy constraint programming, lazy functional programming, programming with active objects, programming with transactions, lazy data flow, sequential object-oriented, event loop, and so on, many paradigms, and they're quite interesting, all of them actually. So in order to bring order to this jungle, we're going to organize the paradigms in a kind of taxonomy where we will relate them depending on which concepts you have to add to go from one paradigm to the next. So this gives a diagram that looks something like this. So we have a very simple first order functional programming, which is kind of the base, the first Turing equivalent, the first powerful way of programming, but we can't do higher order programming. Then we add closures or procedure values, and we get functional programming, which is the higher order programming style that we've shown in this course. And now we can continue building from there. For example, we can add cells, giving sequential object-oriented programming. We can add threads, giving the shared state concurrent object-oriented programming. We can add other concepts such as logging of operations so that we can do transactions, transactional programming. We can go in the other direction. From functional programming, we can go in the direction of logic and constraints. So we can add simple constraint solving, which is called unification. We can add simple forms of search. There's a very specific forms of non-determinism that lets you look at different solutions. And then if you keep going, you come up with relational programming such as Prolog, constraint programming, and you can even add different techniques, make it lazy and concurrent. If you start from functional programming and now you add by need synchronization, which is in fact the thing you need for lazy execution, you get lazy functional programming. If I now add concurrency to this, I have the lazy data flow programming. If I go in the other direction and if I add the threads and the signal assignment first, This is the monotonic data flow programming we saw. So it's another way to call the deterministic data flow paradigm. If we continue now, if we add ports to this, we get the very nice one in the sky blue color one, which is the multi-agent data flow. If we add now a simple non-deterministic choice to the language, we get non-monotonic data flow. If we add certain kinds of synchronization on partial termination, we have interesting paradigms such as functional reactive programming, and so on. So you can see how all these different paradigms are connected to each other. And in fact, there's books and articles you can see showing how these are connected. So I'm not going to explain all of the connections right now. But once you have these connections, we can start to understand the paradigms. So a paradigm, we see, is a set of concepts organized into a kernel language. And each paradigm is its own way of thinking, its own principles of programming, construction, and reasoning. If you have n concepts, theoretically, you can combine them and get 2 to the n minus 1 paradigms. We're not going to talk about the empty paradigm. So there's a lot of paradigms you can define with n concepts. We have not really explored all of those. So I've not explored all of those. There might be some very interesting ones in there that we haven't discovered yet. But since n is much smaller than 2 to the n minus 1, we can concentrate on the concepts and understand the paradigms in terms of the concepts. And in fact, the way we can do that is we organize the concepts in the order for when they are needed. Concepts are not added randomly to a paradigm. They're added according to a certain principle, which we can call the creative extension principle, which we'll explain a little bit later in this lesson. But let me first take a slice of the taxonomy and show some real programming languages. So we start from functional programming, and this is also called strict functional programming. So we have Scheme, ML, Scala are examples of these languages. Also, we have deterministic logic programming, which is also, in fact, a form of functional programming. Now, if we add concurrency and by-need synchronization, we can get the deterministic data flow in the lazy version. We also get non-strict functional programming. So non-strict is a somewhat more general form of lazy programming, which is implemented by Haskell. And if we continue in another way, we add what's called don't care non-deterministic choice. This means a simple choice between alternatives. We get concurrent logic programming. This one is actually kind of a dead end. It was developed a lot in the 90s and then it kind of died out. If we go now from functional programming, we add explicit state and exceptions, we get object-oriented programming, and many languages implement this. If we now add both concurrency and explicit state, we get concurrent object in programming, and again, many languages do it. Here there are the two ways of doing the concurrent programming, either the message passing or shared state. So languages like Erlang and Scala doing message passing, and Java and C++ doing shared state. Now, if we go on and to things that are a little bit less traditional or less well known, if we add another form of choice, which is called don't know non-deterministic choice, which allows to search a space. It allows to go through all the different choices until you find the correct one. Then we get the traditional classic logic programming as in the Prolog language, which was invented in 1972. And this has been generalized to constraint programming. And there are many systems now doing this. Constraint programming is a very active area where one can solve very complex problems with very simple specifications.